So last time we really just talked about the course structure and stuff. Today we'll get into statics. And I guess maybe all of today really will just be talking about vector review. I think that's all we're really going to do. And I'll try to, so you have that document, the vector review document. That is everything you need to know, but I'm going to try to highlight a few things that are going to come up especially often from that. Before we get into that, I want to just talk about kind of where we are in your engineering life. So statics is the first class in, well, I guess really it's the second class in mechanics. The first mechanics class is Physics 1. And from there, you get to statics, and that's us. And statics is kind of a branching point. You can go sort of two directions from here. And in this direction, you start to ask the question, will it break? Will the thing you're looking at break? How's it going to break? Where is the fracture going to start? That kind of thing. And then off in the other direction from statics is how will it move? In the direction of talking about failure and fracture, the first class that you'll take is deformable body mechanics. Most universities call this mechanics of materials. So if you transfer and see mechanics of materials, that's what it's the same thing as our deform class. We call it deform because the U calls it deform, and that's where most of our transfers go. But so we teach deform in spring, and probably half or more of you will take deform this spring. After you've taken that, deform would normally be the last class in this path of topics that you would take before you transfer. And so everything else would be after you transfer somewhere. But if you want to keep studying stuff in this direction, you could go to continuum mechanics. Which is like the coolest name. And then from continuum mechanics, you could either go in the most practical direction, which is finite element analysis. So like deform, continuum mechanics, it's all about like if you apply loads to a body, how is the body going to deform? What are the loads going to be like inside the body? Where is it likely to break? That kind of thing. If you're working for a company and, say you're working for a car company and you want to know in a collision, how is this part of the car going to crumple and like what are the forces going to be inside or whatever. The way they would answer that question is with finite elements. This is a computer approach, and it's the practical way to address these issues. The less practical, but more interesting approach mathematically would just be kind of more continuum mechanics. But no company so this is less practical. no company has people on staff just doing continuum mechanics. If they need calculations done, they do it with computer methods. Yep.
When does like higher level continuum mechanics like that get used if we have like FDA or lots of other stuff?
I mean, it gets used in kind of like mathematical research, and uh,
I guess the question is more like,
right.
are there things that FDA can't solve?
Not really, no. This, I only bring this up, maybe other people who are drawing a diagram like this wouldn't even mention that you can keep doing continuum mechanics. I happened to come from a PhD department where where that was the kind of stuff we did. So, but it's really it's a lot like math or applied math or whatever, and less like really just trying to get a solution, Okay, so, and then this stuff can go, you can keep going in these directions. But this is kind of the flow of if you're working on determining fracture and failure of materials. In the direction of how will it move, the next class you would take is dynamics. And I teach that in the spring. So a lot of you will take that from me. The one you take first deals mostly with Newtonian dynamics, just using Newton's laws. And then from your first class in dynamics, now again, this is about the point where most of you would transfer. You could go into more dynamics. The next class in dynamics you take after you transfer probably emphasizes Lagrangian dynamics, which is like energy methods. And then after you take dynamics, Jesus, you can take fluid dynamics. And there's a lot of interesting stuff in fluid dynamics. And the math is crazy, can get crazy in fluid dynamics. So that just goes on and on forever. And I think a lot of people think fluid, they think liquid, but fluids deals with any substances that can flow, that doesn't have like a starting state that it returns to if you remove all the forces. So this includes liquids. What? So gases, exactly. And so fluid dynamics is something like if anybody who's going into aerospace applications will deal with a lot of fluid dynamics.
You would use fluid dynamics for air resistance.
Exactly. And any kind of aerodynamics. And so any kind of aerospace applications while you're still in our atmosphere. Once you get out of the atmosphere, then suddenly fluid dynamics doesn't matter anymore because there's no air. Okay, so that's kind of where we are and where you're going if you're going to focus on mechanical, aerospace, civil, the mechanical parts of civil engineering, that kind of stuff. And in statics, the types of calculations that we're going to do so the types of calculations that statics is useful for the first one is structures. We're going to do a ton of structures. So an example of that would be, say you have something like this, where these different pieces are held together by joints. And let's say you have some known force applied, and you want to know what are the forces applied to the members by the joints. These are important questions for knowing what kind of materials you need to build stuff out of, how thick you need the walls of your machines and stuff to be. And so that's the most straightforward application. Yes?
What's the difference between the forces applied to the members by the joints and the forces applied to the joints by the members?
Yeah, well, that's something that you should always keep in mind, and it's easy to forget that that's an important thing to think about. Newton's third law is the answer, you know. So if one of those joints is applying an upward force to the member of 500 newtons, then the member is applying a downward force of 500 newtons to the joint. But you always have to think about what is the thing that I want to calculate the force on, you know. Another example of a structure's calculation would be like so this is like a person standing here. In agony. That knee bend's getting tiring. But anyways, handsome. What are the muscle forces required in whatever, let's say the soleus, just some muscle. Okay, you can imagine that calculations like this have medical applications and sports science applications and stuff like that. So, and you can use the same approach that you use in engineering structures to calculate muscle and bone and joint forces. And then the second thing we're going to do a lot is internal loads calculations. And so a simple internal loads calculation would be like this. Let's say that you have a beam that's connected at this end over here. And let's say there's a roller here. And you have a force, some known force there and some known force here. Let's say at each point in the beam, what are the loads applied by the surrounding material?
Would that be like if you built a really tall building, making sure the bottom floor and the front side of the all the other one?
Yeah, exactly. And so this is like the first step towards stress and strain analysis, which is what we'll do in deform. And so this is kind of like the first step towards determining where fractures are going to happen. And we're going to get into these calculations this semester. Okay, so now let me give a little bit of a, well, let me first take questions on the vector review problems, and then I'll get into, outlining some of what's important in the vector review after that. Does anyone have any questions you'd like me to do from the vector review? Yes.
I have never used the brackets.
Yeah.
Information. Could you explain it?
Yeah, sure. Yeah, well, the basic principle is just, okay, so here's the vector review. So if you're used to notation like this, that exact same vector you can just represent as A, B, C. Oh, that's a different one. Let's see. I just got this new replacement computer, and so it's going to take me a while to get used to like the hand strokes and stuff. Okay, so the top element is always the X component. The second element is always the Y component. And if there is a third element, then that's always the Z component. We're going to do a lot of stuff in 2 dimensions. So, God dang it. Okay. So in 2D, you'd just be dealing with an X and a Y component. So you can also just sometimes see it like this. And the meaning of that is the same as A, B, and then 0 for the Z component. Yep.
So when I was reviewing, I was sort of, I guess I understand what the cross product is doing and how to do it, but I guess I don't really understand one where like how you go from wanting to get something perpendicular to then doing that with vectors, and then also how to like prove that that works, which I guess is maybe outside of the scope of the class, but
yeah, how to prove that it works.
it obviously does, but
Right.
You went over that taking Calc 3 yet? Or that was covered in Calc 3?
Okay, well, I will definitely talk about the cross product. One thing about the cross product that I want you all to know is you should get whatever calculator you have, you need to get set up so that you can just do those cross products on your calculator. On an 89 or an Inspire, it'll just do it for you, and I'll talk about that later today. On an 84 or an 83 or an 86, you'll have to enter in a program, but I can help you do that. It's quick and easy. Okay, so but let me just keep going with sort of the steps that I was going to follow, and we'll get to that pretty quickly. So the first thing you need to know about vectors is that you can always think of vector components as the coordinates of the head of the vector when the tail is at the origin. So, for example, let's say that you have a vector like this that has a length of 1.5, makes an angle of 30 degrees with the horizontal, and you want to calculate the components of that vector. For fuck's sake. So the way you would do that is you would think of the coordinate system, put the tail of the vector at the origin, and then it's just a problem of calculating the coordinates of the head. You can always do that as, so think of so we already know that the length is 1.5. Take the counterclockwise angle, from the coordinate system's positive x-axis to the vector, and I'm going to call that theta. Then the components of this vector, u, are the length times the cosine of that theta, and the length times the sine of that theta. In this case, the theta that we want, we start at the positive x-axis, go counterclockwise to the vector, and that's our theta. You can also go clockwise and call it a negative angle, and it works just the same. And so in this case, you got 1.5 times the cosine of 30 degrees, 1.5 times the sine of 30 degrees, and that gives you 1.299 for the x component and 0.75 for the y component. And you always can also set up your right triangles and use SOHCAHTOA to calculate the legs. But this will always work. And the nice thing about it is it's very programmable. So like in the long run, you're not going to be doing hand calculations at jobs or in research projects or whatever. You're going to be using what you know about doing hand calculations to write computer programs. And this approach where just wherever that vector is, you go counterclockwise from the x-axis to the vector is really fits easily into computer programs. So one thing that you'd need to be able to do is manipulate vectors in your calculators. So let's talk about that for a second. Does anybody here have a graphing calculator that's not Texas Instruments? Okay, what brand is yours? Casio. Okay, well, we should just talk outside of class sometime and we can figure out how to program that and stuff. So if you have a TI-83 or an 84 or an 86. The way that you enter vectors is you get into the matrix environment and you go to edit and you choose your dimensions. When we're dealing with vectors, your dimensions are going to be either 2 by 1 if you're doing two-dimensional calculations, or 3 by 1 if you're doing 3D calculations. So that's one way you can do it. If you have an 84, an 86, or an 89, you can also enter your vectors as square bracket, and then square brackets for each column in the vertical, or sorry, for each row in the vertical matrix. So another square bracket, and then A, square brackets B, square brackets C, and then square bracket to end the vector. So this would be, this is your X component, your Y component, and your Z component. And then, so you do this, and if you want to put that into a variable, if you want to name that thing, you use the store function. It's almost always in all of them, I think, at the bottom left somewhere, and it looks just like an arrow. So something like that, and then just put it into whatever letter you want to put it into. So this is the store function. So if you have an 84 or an 86, I think you have both of these two options for entering vectors. If you have an 83, you have to do it in the matrix environment. And then third, if you have an 89, you have this additional option that's, instead of using square brackets for the rows, just separate the rows with semicolons. So A, B, C. Just a few less pen strokes. Okay. And then the last one is if you have an Inspire, they have sort of their own matrix environment. So they have this thing that looks like doesn't it? It's like sort of like this.
Well, that's the button.
Yeah, the button.
Oh, yeah, that also just pulls it up.
And then if you press on that, then you can choose, do you want a matrix this size? Or do you want it this size? And so you just have to choose whether you want 2D or 3D and enter your values in there.
And the one with 9 boxes, that's like the custom one, and you pick how many, right?
Yeah, but we're only using vectors, so you won't need that here. Well, I'll talk a little bit about some matrix calculations later, but pretty much this is all we're going to be doing. Okay, and so if you, in all of these, if you define a matrix and put it into a variable that you call U or something, and then do another vector and put it into a matrix you call V, and then enter U plus V. Your calculator knows how to add matrices. It knows how to multiply matrices by numbers. And so you don't really ever have to do those calculations yourself. But I do want to talk about what those things mean. You should just have those in your head. So here are some vector calculations. The first one is, what does it mean to add two vectors? So if we have A, B, C, and we're adding it to D, E, F, the sum is, you're just going to be adding the two X components, adding the two Y components, and adding the two Z components. If you're multiplying a vector by a number, so let's say we're multiplying the number D times the vector A, B, C. The product is dA, dB, dC. And again, your calculator will do that for you. And then there's two ways to multiply two vectors together. So now multiplying two vectors. The first one is the dot product. And the dot product, you'll also sometimes see referred to as the scalar product. Or the inner product. And you can think of it as having two vectors as input, and then just a number as an output. So the answer is not a vector, it's a number. The fact that it has a number output is the reason that sometimes people refer to it as the scalar product, because scalar is like another word for a number. It's a matrix with a size of 1. So the dot product between a vector A, B, C and a vector D, E, F is you multiply the two X components together, multiply the two Y components together, multiply the two Z components together, and then just add those up, and it gives you a number. In the TI-89 or the TI Inspire, there are built-in functions to do this. So you can just go lowercase dot, uppercase P, put in your two vectors. So A, B, C, comma, D, E, F. Hit enter and it'll give you that answer. If you have a 83, 84, an 86, or a different company's calculator, you're going to have to program something to do the dot product. And it's a one-line program. It's easy to write. So talk to me and I'll help you get that into your calculator. It really would be, we won't use dot product a ton, but with the cross product, you absolutely don't want to be doing the cross product by hand in this class. It's just going to add a lot of unnecessary time. So that is the first way to multiply two vectors. And the second one, my computer every once in a while doesn't recognize the pen for a second. Okay, so the second one is the cross product. This is the one we're going to use all the time. You sometimes see this referred to as the vector product. Or the outer product. And the way it works is this: if you have A, B, C crossed with D, E, F, you're going to get 3 component values from this. For each component value, you're going to go, so to get the X component, you're going to cross out the X components. And then you're going to go, this is why it's called cross, the cross product, I guess. Now you'll go cross multiply those, minus cross multiply those. Okay. So your X value is going to be BF minus CE. Now to get the Y component of the answer, you'll cross these out. And you'll go this times this minus this times this. Oh, let me erase that first. So we'll go A times F minus C times D. And now there's one more step with the Y component. You see this in vector stuff all the time. The Y component just always has to be a little different. It's just always got to be a little pain in the butt. You know, there are people like that and there are components like that. So the Y component, once you do that cross multiplying thing, you take the negative of it all. Jesus. This fucking thing. Okay, so like that. And then the last one, the Z component, cross those out. Then this times this minus this times this. So you get AE minus BD. And if you have a way that you learned in a math class or something that you like better to think about it, that's fine. Really, like I said, I don't want you to have to do this by hand anyways, you know. I want you to have a way that you can just punch it into your calculator. The same way you would a square root, you know. one thing I want you to notice is in 2D, so let's say that we have the vectors A, B, 0, and we're crossing it with D, E, 0. So those are two-dimensional vectors. If you cross out the x values and then go B times 0 minus 0 times E, you get 0 for the x component. When you do it for the y component, you get 0 again. So the only component that's non-zero is the z component. And to get the z component, cross out the zeros, and then it's AE minus BD. Okay, so we're going to do a lot of two-dimensional calculations, and notice that in two-dimensional calculations, you only have a z component, and so a lot of times we won't even write it as if it's a vector. But it's really important that you remember that a cross product is always a vector. Okay, like you start to think of this answer as just whatever AE minus BD is. And you start to think of it as just like a number, a scalar answer. But remember that it's really a z component of a vector. Okay, notice the output vector is perpendicular to both input vectors. And that it satisfies the right-hand rule. Okay, so let's say that we have a vector u that's going this direction, and we're crossing it with a vector v that's going into the page. I don't know if you've seen this notation before, but I'm going to use it from time to time. Think of, if you see a circle with an X in it like that, think of that as the feathers of the arrow. So that says that the vector is going away from you. Okay. If you see a circle with a dot in the middle, think of that as an arrow where you're looking right at the point. So that's coming out towards you. Okay, so we have one vector that's going that way and one vector that's going that way. So what's the direction of the cross product of these two vectors? So let's say we're going to go u crossed with v. So we're going to take our right hand and we're going to start with our fingers in the direction of this u. Okay. So our fingers are pointing in the direction of, that is the left hand, thank you. Don't do that. It gives you everything backwards. So the right hand, we're going to go So you're going to start with your fingers in the direction of you. And you're going to hold your hand in such a way that your fingers will, imagine your fingers don't bend backwards, they only bend forwards. So you have to hold your hand in such a way that you can bend your fingers now from this configuration to line up with V. So then you'll go like, uh, okay, your hand got really bony all of a sudden for some reason. Okay, so now your fingers are pointing into the page in the direction of that vector V. And since you put your hand in a configuration that allowed you to start at U and end up at V, that tells you that the direction of the product is the way your thumb is pointing. So the cross product direction is up. Yes.
It might have said it, but I forgot if it did. Is the cross product commutative?
No, it is not. It is so, and actually, that's one of the things I'm pretty sure I want to say here. Okay, so I have a list of things that I want you to remember about the cross product, and that's one of them. Before I do that, I gotta hurry. If you have a TI 89 or Inspire, it will do the cross product for you. So enter in cross, capital P, put in the two vectors, and it'll just spit out the answer for you. If you have any other kind of calculator, come talk to me after class or in office hours or something, and we'll get this working on yours. It's easy to do. Okay, so a few things to notice about the cross product. So first, remember that the y component always has to be the weird one. That's how it's going to be for the rest of your mathematical life. So don't forget to add that negative sign to what you get from cross multiplying for the y component. Second, remember that the output of the cross product is perpendicular to both input vectors. That's going to be a really useful fact for us. The cross product of any two parallel vectors is 0. we can use the cross product to define acceptable coordinate systems. To us, an acceptable coordinate system is a right-handed coordinate system. So the requirements for a right-handed coordinate system are that the x-axis crossed with the y-axis is equal to the z-axis. The y-axis crossed with where did that go?
Is the palm rejection not working?
Yeah, it's because I'm left-handed and I didn't set it up, I think. It'll work eventually. Where did that go? Solutions. Oh, okay, here we go. Okay, the y-axis crossed with the z-axis is equal to the x-axis. And then remember, the y-axis always has to be the weird one. The y component has to be the weird one. So I cross k is equal to negative j. And then the last one is that the order matters. In the cross product. So A cross B is negative B cross A. On the other hand, so in parentheses, I'll say, on the other hand, with the dot product, the order doesn't matter. A dot B is equal to B dot A. Okay, so if you switch the order of operation of the cross product, you get the negative answer. Okay, any questions about that? Yes.
The negative for the B or around the whole thing?
It's the same. It means the same thing. Yes. So you can move negative signs, pull them through, and whatever. Same with scalars. You can pull in, pull out.